Good morning, everyone. My name is Rahul Rugani, and I'm a PhD student at the University of Southern California. Today I'm going to talk to you about safe construction in space and how to use swarms of small satellites for in-space manufacturing. In this decade, we're entering a new era of in-space manufacturing. New technologies, new capabilities, and new demands are leading to advances in on-orbit servicing and space robotics, allowing for the in-space construction of objects. One day, we hope to build objects entirely in space, allowing for structures larger than what we ever conceived. Although this was once the realm of science fiction, many companies are working to make this a reality. Although current on-orbit servicing capabilities use large monolithic robotic spacecraft, I'm proposing a method to use a swarm of dozens, potentially even hundreds, of small spacecraft. Swarms operate analogous to a colony of bees, with each individual spacecraft performing its own dedicated task, culminating in the successful execution of a large and complex operation. These swarms are redundant in nature because if any spacecraft in the swarm fails, it does not result in the failure of the mission, as the other spacecraft can still remain to complete the mission. The current state of the art for on-orbit servicing is the Northrop Grumman MEV-1, their mission extension vehicle. This was used earlier this year to dock with Intelsat 901 in the graveyard orbit above geostationary orbit, and this proved that on-orbit servicing is possible and it can be done safely. Safety is paramount in on-orbit servicing missions, as space is a shared commons, and debris created will affect all parties. The method I'm proposing for creating swarm trajectories has safety as a top priority in the optimization process. Rather than discuss the full autonomous swarm system, I'm going to focus today on the trajectory generation method that I'm using. This method uses genetic algorithms to evolve a set of initial conditions into a solution of relative motion trajectories for a swarm by applying constraints. This allows us to generate trajectories for a swarm of spacecraft that have no collision risk over a specific prescribed amount of time, in this case 24 hours, and also minimize the insertion delta V and the station keeping delta V. The goal is to find repeatable relative motion trajectories that can also be tailored to the constraints of each member of the swarm. Some spacecraft may need to get very close to a target satellite, whereas other spacecraft in the swarm may need to remain at a constant distance for imagery or sensing purposes. This set of algorithms is able to handle these various tasks. In order to efficiently generate and optimize trajectories for the small satellite swarm, the genetic algorithm process alone is not enough to be able to account for all the deviations. To be able to account for gravitational and other perturbations using high-fidelity models, a two-stage process was developed. Stage 1 uses a genetic algorithm solver to generate a set of trajectories satisfying the swarm constraints using the linearized Clohessy-Wilshire equations for relative motion trajectories. As these equations are linearized, they can be computed very quickly, and this allows us to go through many iterations in a very small amount of time. However, the solution yielded from the linearized case will not form closed trajectories when perturbations are applied to these initial conditions. This is where stage 2 comes into account. In stage 2, we feed the solution from stage 1 into the same genetic algorithm solver, but this time using a nonlinear numerical integration propagator with perturbing accelerations atop the equations of motion of relative two-body dynamics. This allows us to use the solution from stage 1 as a guess for stage 2 and quickly solve the stage 2 nonlinear case as well. This can take into account not only the Earth's J2 perturbations for LEO cases, but also higher order perturbations such as the fourth order spherical harmonics of Earth's gravitational field for taking into account east-west perturbations at geo-altitudes, as well as solar radiation pressure and sun-moon perturbations, which are prominent at geo altitudes as well. Now that we've generated trajectories using the two-stage solver, we need to figure out whether these trajectories will collide with each other. To do this, we need to figure out the conjunction probability, and this comes into account using sensor fusion. By combining the data from sensors on board each swarm spacecraft, ranging, LiDAR, etc., and applying them to a common filter, we can reduce the uncertainty covariance on the client object, in this case, in the figure on the right, more than a simple common filter would be able to do that with a single sensor. Once we have the covariance matrix for the position error of each spacecraft, we can compare them to each other to figure out which spacecraft are in a collision threshold. If any spacecraft are found to have any conjunction probability greater than 0, then the swarm is deemed to be invalid, and we will modify it using further optimization processes to yield a satisfactory swarm. The sensor fusion Kalman filter is very similar to a standard Kalman filter, except for the fact that after we do the propagation step, the update step is performed multiple times, once for each sensor. Given the fact that the main computational overhead in a Kalman filter is the propagation step at each time step, adding multiple update steps does not increase the computational time significantly. Thus, for very little computational time, we can significantly increase the accuracy of the position knowledge of each spacecraft by reducing the covariance of the position error of each spacecraft. These covariances are then used for the conjunction analysis between multiple spacecraft. Running this whole system through for a set of five spacecraft, we get the following set of trajectories on the figure on the left. These trajectories are repeating over an orbital revolution with some error due to the insertion error. And of course, there will be insertion errors because no spacecraft has perfect sensors and perfect thrusters, so they can't perfectly achieve the trajectory computed by the simulation. However, this is taken into account, as the figure on the right shows what would happen with a small insertion error, and you can see that there's a drift in the position of each spacecraft. However, this can be taken into account by station keeping maneuvers, and for LEO cases, this is taken into account by using less than 1 meter per second per day per spacecraft, which is more than within the limits of a small satellite. Now, applying this to a scenario for in-space manufacturing, for example, on the right, an in-space construction site using 10 spacecraft, we can see that we can apply constraints on the spacecraft for them to have different roles, such as close quarters rendezvous in the red zone, comm relay in the yellow zone, and a staging area in the green zone. And this is applied by tailoring the constraints in the genetic algorithm for each of the spacecraft in the swarm. You can see that on the left, the staging area has spacecraft that are maintaining a distance of 5 kilometers, range from the client spacecraft. The spacecraft in close quarters are within 500 meters of the client spacecraft and can go closer. And the comm relay is within direct line of sight of ground station at all times. This shows that an in-space construction site can be created using this software and algorithms, and this is a viable method. Finally, I'm going to talk to you about how this scales with larger swarm sizes. With regards to scaling the algorithm, the conjunction deconfliction process takes the greatest amount of computational time. This scales on the factor of n squared, where n is the number of spacecraft in the swarm. The figure on the right shows experimentally how this scales using multi-trial averaging over 100 runs for each swarm size to remove the effects of pseudorandom initial conditions. This is run for swarms of size 3 through 25, showing as follows a parabolic increase in line with the theoretical value of the order of n squared. Future work will strive to reduce the computational burden so that this can be run in real time on board the spacecraft. In conclusion, although in the near term the system will require ground intervention when the swarm deviates from its planned trajectory, the long-term goal is to develop an autonomous system that can accept and remediate failures of one or more of its members in real time. While not possible at the moment, we're striving to make real-time trajectory generations for N spacecraft possible on board the existing computational hardware on the spacecraft by using machine learning techniques and optimizing the software for different processors. The long-term goal is to be able to have a fully autonomous system such that a swarm could be sent to Mars and autonomously build a large aperture communication system in orbit without any intervention from a team on the ground on Earth. Thank you very much.